Hello everybody, in this video I will show you how to solve circuit with multiple current or voltage source. We will do this by using the superposition theorem, which states that in a circuit with multiple voltage or current source, the individual effects of each source can be assessed separately and then combined algebraically for obtaining the full response of the circuit. So let's do this with an example and consider the circuit here on the left, in which we have three sources: a current source I, a voltage source VA, a voltage source VB, and then 5 resistors. We have all the values here of the problem, and so we start solving the problem. First of all, we'll set voltage drops and current direction in all the circuit. So I set my plus and minus and arrows in all the resistors. And I don't give any name here in the circuit. I don't write down any name here in the circuit because I want to keep it simple to see it. But basically, we will call this voltage drop here V1 and this current I1. The voltage drop here V3 and the current I3, and so on for all the resistors. Okay, so let's see how we consider the individual contribution of each source to the circuit. We have to keep one of the source at a time on and turn off the other two. So we will have basically three cases. Let's start with the first one that I consider. The first one that I decide to consider is the one in which I keep on VA and I turn off the current source I. When I turn off a current source, I substitute the current source with an open circuit. So I now is an open circuit. When I turn off a voltage source, I substitute the voltage source with a short circuit. So now VB is a short circuit. This is the case one for VA on. And now let's consider the case in which we have VB on, just VB on. So we turn off the current I, we turn off the voltage source VA, and we solve the circuit as in the previous case. Finally, we have the third case in which we turn off both voltage sources, and we keep on the current source. So we have VI off and VB off, both with a short circuit. So the next step is to solve each one of these three cases, and then adding up all the contribution from all the current and voltage that we obtain in each case. So in the following of this video, I will solve one at a time of these three circuits, and then I will add up in an Excel file all the contributions. So for the case in which we turn on VA, I will write down all the voltage value and the current value, and so the same for other two cases, VB on and I on, and I will sum up all this contribution for each value of the circuit so that I obtain the final and full response of the circuit. Okay, so let's start with the first case and solve the circuit for VA on. This was the circuit that I showed you before, and we will solve this as I showed you in the previous video. So we first of all will check for the equivalent resistance of this circuit. So we see that the battery VA actually splits into two. One is a cable that goes nowhere, so no contribution, and then I find R1, then R3 going nowhere, and then I split into two, R2 from one side, R4 other side. After R4 follow R5, and then R2 and 5 join together and come back to my battery. So basically the equivalent resistance here, okay, where R3 give no contribution to the circuit is given by R1 plus R2 in parallel with the sum of R4 plus R5. We have the values here of the resistors, so we have R1 is 2 kilo ohm, R2 is 2 kilo ohm, R4 and R5 are 1 kilo ohm each, so this is a parallel between 2 kilo ohm and 2 kilo ohm, which is 1 kilo ohm, plus 2 kilo ohm over 1, so this value is actually 3 kilo ohm. So the battery see 3 kilo ohm value, and for a battery of 6 volt VA, as my data told me, so I will have a current flowing here, flowing in, exiting the battery, a current of 6 volt, 3 kilo ohm, so 2 milliampere in this direction. 2 milliampere current on a resistor of 3 kilo ohm gives me 4 volt with this polarity. If I have 6 volt with this polarity plus and minus here, this mesh, I must have here 2 volt. And 2 volt over a resistor of 2 kilo ohm corresponds to 1 milliampere flowing in this direction. The 2 milliampere comes into this node. I have no current in R3. I have 1 milliampere here, so I will have 1 milliampere also in this branch, which actually is the same current here, which is still 1 milliampere. 1 milliampere flowing into 1 kilo ohm gives me 1 volt. 1 milliampere flowing into 1 kilo ohm gives me 1 volt. So I have all the values of the circuit. So let's fill now the Excel table. So we have V1, which is 4 volt, and if we check the polarity of this voltage with the polarity that we have stated at the beginning of the problem, we will see that it's the same. So we put a positive number. It's 4 volt in the same sense, the same polarity that we choose at the beginning. So V1, 4 volt, actually all these voltage are in the same polarity as we have decided before. So I have 4, 2, 0, 1, 1. 4, 2, 0, 1, 1. 0 volt, 0 volt in R3 because there is no current flowing here, so there is no voltage drop. And for a current I have I1, 2, I2, 1. So I have 2, 1, 0, 1, 1. 2, 1, 0, 1, 1. Okay, so this is basically the contribution of my first case. Let's see now the second case in which we turn on VB. So let's go with the second case in which we turn on only the voltage source VB and we turn off the current source and the other voltage source. So let's look at the circuit and we see that VB go into R4, then we split here R3, and then we split also into two branches. One is R1, the other one is R2. Then these two guys combine back here, they join again. And then we have R5, which come back to the battery. So I have 5 here, and that's it. So here, all these equivalent resistance. We also have a cable coming out from this branch here between R1 and R5, but actually this go nowhere, so this gives no contribution. So the equivalent resistance by the battery is equal to R4 plus the parallel between R1 and R2 plus R5. So we have R4 and R5, which are 1 kilo, R1 and R2, which are each one of them 2 kilo. In parallel, 2 kilo with 2 kilo is 1 kilo. So this value is actually 3 kilo. I have done another video about equivalent resistance. Watch it if you have not clear this interpretation here, this equivalent resistance. So the battery is 3 kilo here. The battery is 3 volt, so 3 kilo and 3 volt give me 1 milliampere, which flow in R4 and produce a voltage drop of 1 volt, because 1 kilo R4 is 1 kilo. It's 1 milliampere current flows through R4, so I have 1 volt voltage drop. Then I have this mesh here, actually this full mesh that we see here is given by 3 resistors, R4, 4 resistors, but I can say R4, which is 1 kilo. Then the parallel of R1 and R2 here, which is also 1 kilo, because it's the parallel between 2 kilo and 2 kilo. And then another 1 kilo here. So if I solve this mesh, I will have a voltage divider, and so this 3 volt of VB will fall 1 volt here, 1 volt, let's say here, which is the same that's saying I have 1 volt here and also 1 volt here. Is the same from this point to this point, or for this point, or from this point to this point is exactly the same. So I have 1 volt here and 1 volt in R5 with this polarity that then sum up and give me 3 volt here. So 1 volt here. And then as R1 is 2 kilo, I have here 0.5 milliampere. And here other 0.5 milliampere. With these 2 half milliampere, they combine back and give me 1 milliampere here, which is coherent with the fact that R5 is 1 kilo ohm and I have a voltage drop of 1 volt here. You can solve this with the meshes, but this is the result, and I want to show you that all the circuit must be coherent. Okay, so you also can check that this makes sense or not. I have 3 volt here that's sharing 1 volt, 1 volt, and 1 volt. I have 1 milliampere here that's split into half milliampere and half milliampere, and then combine back to 1 milliampere. So I can put this value in my Excel table and continue with my analysis of the circuit. So in this case, I have, let's say V1 now. If I check my original polarity and direction of currents, I see that now the polarity and the current direction they are both opposite to my first statement. So we have to put here a minus sign. And actually also therefore the current and the polarity are opposite to the sign that I choose at the beginning. This thing happens also for R5. In R3 I have nothing. And in R2 actually the polarity and the current direction are the same then of the ones at the beginning of that I stated at the beginning of the problem. So I will have to, for the voltage I will put -1, +1, 0, minus 1. Again, -1, -1, 1, 0, -1, -1. For the currents, I1 will be minus 0.5, I2 will be 0.5, I3 will be 0. I4 will be minus 1 milliampere, and I5 will be minus 1 milliampere. So I am done with the second case. Let's go now to the third case. So let's start the third case, in which we turn on the current source I and we turn off the other two voltage sources. So in this case, we can draw our equivalent circuit like this. We have the current source I, and then we find R3, which then splits into three branches. We have R4, we have R2, and we have R1. Then R2 and R1 combines back. After R4 we have R5, which then join the two other branches and come back to the current source here. So basically we can write down the equivalent resistance are R3 plus the parallel of R1, R2, and the sum of R4 plus R5. I have written this equivalent resistance here for clarity. If we think about it a little bit, we will have 2 kilo, 2 kilo, and 2 kilo. So this is 2 divided by 3. Why? Because actually 2 kilo and 2 kilo is 1 kilo, and the parallel of 1 kilo with 2 kilo is 2 divided by 3 kilo. Anyway, you can do the calculation slowly with this data, and you will find out that the solution is 8 divided by 3 kilo. So we have now the resistance seen by the current source. So we can, if we know the current, which is 0.6 milliampere, and we can calculate the voltage drop at this terminal, so between these 2 points, which are the point of the equivalent resistance. So we have from this voltage drop here with the current entering this terminal, we can call this voltage drop, which actually in this circuit correspond to this voltage drop here between this point and this point, we can call this thing Vx. And we can say that Vx is actually equal to 0.6 milliampere, the value of I, divided, multiplied the value of the equivalent resistance that we just found. And so we know that Vx is actually 1.6 milliampere, 1.6 volts. I write down here 1.6 volt, this voltage difference. We know also that this current I, which is 0.6 milliampere, enters R3, which is 2 kilo. So we have that 0.6 milliampere times 2 kilo gives us 1.2 volt. So we have this voltage drop here. And by looking at this mesh here and remembering that we must have a zero sum of all the voltage drop, taking into account their polarity, we can say that 1.6, 1.2, we must have here with this polarity 0.4 volt, because 0.4 volt plus 1.2 volt will give us 1.6 volt. So we can calculate now the current in this resistor, which is 0.4 volt divided by 2 kilo, so we have 0.2 milliampere. Okay, 0.2 milliampere. Also, we can say that the voltage drop between this point and this point, which is 0.4 volt, is the same voltage drop between this point and this point, also this point. So we know now the voltage drop on R2. We can say that in R2 we must have plus minus 0.4 volt. And so the current flowing in R2 is 2 kilo, the current flowing to R2 will be 0.2 milliampere, because we know the voltage and we know the resistor. So the current coming from this side, 0.6 milliampere, split into 0.2, 0.2, and on this side must be also 0.2 milliampere. So we can find the voltage drop here, therefore, which is 0.2 milliampere times 1 kilo ohm. We have 0.2 volt here. The same current flowing into R4 goes through R5. So we have also here 0.2 milliampere, and we have here a voltage drop with this polarity, which is given by 0.2 milliampere times 1 kilo, which is 0.2 volt. Okay, so we have solved the full circuit in the third case, in which only the current source was turned on. Now we have to translate this information to our Excel table, so we can sum up all the contribution and find the full solution of the circuit. In moving this value to the Excel table, we have to take into account the original signs and direction that we put at the beginning of the problem. So rewind the video to the beginning if you want. I don't want to switch between different pages, or just trust me, and we can say that V1 actually is opposite to the polarity that we choose, so we have to put minus 0.4 volt. In this case it's 0.4, and the other are all they all agree with the polarity and current direction is stated at the beginning. So we have in V2 we have 0.4, V3 we have 1.2, V4 we have 0.2, and V5 0.2 also. For the currents, we have I1, which is minus 0.2 milliampere, so minus 0.2 milliampere. I2 is 0.2, I3 is 0.6 milliampere, and I4 and I5, they are both 0.2 milliampere. So with the contribution of all the three cases that we have analyzed, in which we turn on one source at a time and we turn off all the other sources, just let me put here volt and milliampere, so we can sum up all the contribution and we find the solution.